So in the aspect of her work is an assistant professor of University of California, Irvine, like a staff scientist. He worked at Okinawa Institute of Science and Technology, OIS, postdoc in Max Planck Institute of Solid State Research, Stuttgart, Germany, and another postdoc in Leibniz Institute of Solid State and Material Research Unit. So her research interests include fluid magnetism, spin orbital physics, multiferroic materials, and topological phases of matter. So it's an honor for us that you can present in our research group. So the exposition is titled C2 or not C2, Symmetry Protection of Triple Band Topology. So you could start, Professor Judit.
Okay, can I share the screen? So
yeah,
let's see, I think I can.
Right now.
Yes. I will share
Always
it.
when people present other people, always we say it's an honor for us to have you here. But today, that's more than true.
That's so nice of you to say. It's an honor for me to be here too.
This presentation, because she's amazing in this.
No, please don't say that. That's very nice of you.
Please enjoy this presentation, guys at University of Valle, guys and girls at University of Valle, guys and girls at University of Pamplona. Thank you, Professor Judit. Really,
thank you. Thank you so much for the kind words and for the introduction. It's my pleasure to give this talk. I'm sorry if it's going to be a little bit, unprepared, because it's been really crazy towards the end of the quarter here, and yes, like life was not very easy, I guess. So I guess most of you are students. Is that true? Graduate students and so on?
Yeah, so there are some students. There are some students, and there are few professors.
I see.
And so me, but Karen is not here today, but she will watch the lecture once more with some of her students. So
okay, I see. I hope it will be okay. But in just in case, because there are students and this is a seminar, I would like to encourage you to ask questions, and I will go slowly. I don't know how much time I have, but I think it's less than an hour.
Don't worry.
Okay, it will not be very long, and I will try to go slow, but as if someone has any questions, please don't hesitate to just yell in, because I'm not very good with Zoom and I never see when someone raises their hands. So please just ask the question, just unmute yourself.
I will control the questions with Pedro.
Okay, cool. Thank you so much. Right, so this is a small project about whether it is plausible to think about Z2 topological bands realized by monetic excitations or not. So we started this project some time ago when I was still in Okinawa, which was very, very nice. I don't know how I can, okay, yeah. But actually Carlo Pence was my PhD advisor back in the day. That was really long time ago. And we still collaborate together a lot. And at that time, when we were thinking about this project, Carlo was visiting Okinawa and I was working in Nick Shannon's group. And Andreas Thomassen was a shared student between me and Nick. And today, actually, Andreas is already Dr. Thomassen, and he's working for a company on quantum computations and quantum information. So he moved on from academia, but he still does quantum-related research. And the stuff that I'm going to talk here about is mostly his work and like a big part of his PhD thesis. All right. So with that, I would like to start kind of at the beginning, when topology became very important in condensed matter physics. It's really nice because condensed matter physics is over 100 years old. And And most of the really important advances, or the ones that we actually call like very important now, were discovered about 15, 20 years ago. And it kind of started with the integer quantum Hall effect, and that it has something to do with topology, or the band topology of these systems. And I would like to go back all the way to Haldane's model. Let me just, I'm sorry, I will have to move everyone from the side, because I see this view, but I see you guys as well, but I don't see what I'm pointing at. Okay, so I go back to Haldane's model, which is a nice kind of toy model, a theoretical toy model. When we consider a honeycomb lattice, I guess you all know this model, but just for completeness sake, I will still say a few words. So we consider this honeycomb lattice where electrons can propagate, and there is no interaction between them. So it's just a hopping model. And if we now add second neighbor hopping terms that are complex, then these will contribute to the formation of non-trivial band topology. So without these second neighbor hoppings, we have a band structure that looks something like that. And as soon as we have those second neighbor complex hoppings, we will develop a band gap that was actually closed at the K point before. And we will also, in an open system, have edge modes that are collapsing this band gap. And correspondingly, in the bulk, we have, because of this non-trivial band topology, we have finite Chern numbers, and these Chern numbers are kind of the topological indices that characterize this, the topology of the system. So I don't know how much you know about that. I certainly am not an expert, but how I like to think about it is that we have something like a curvature that is very similar to the curvature in geometry. And instead of integrating this curvature over a closed surface in real space, we integrate it over a closed surface in the reciprocal space. And once we do that, we get an integer number, and this is called the first Chern number. That is going to be the topological invariant in the case of this Haldane model. Okay, so that was kind of an initial point for all this development. And if you wanted to, look at whether a system has a non-zero Berry curvature, for example, or not, then we can measure Hall conductivity, and what we will see that we have these integer Hall conductance, and that is actually the Chern related to the Chern number. So these, these kind of topological properties, they show up in experiments as well, and there are physical properties that are kind of related to them. So it's not just a mathematical abstraction. And now let's see what happens. So if we go one step further, and instead of spinless electrons that was considered for the Haldane model, we now consider spinful electrons. And that actually adds additional degrees of freedom. Yes?
Excuse me, one question.
Yes.
Maybe for the students, could you explain just in two phrases, what do we refer to when we say Z2? That's a topological classification, or what kind of classification is this?
Yes, it's a topological classification. So for example, if we go here to the Chern numbers, that is a Z classification. And this number here, this can take integer values that are actually the plateaus that one can see in the Hall conductivity times this universal constant here, right? So then this is kind of the quantum of conductance times the Chern number, which is a mathematical abstraction. It's kind of this, this topological invariant, but it's also the physical quantity that you measure, right? And these numbers can take integer values, so we call this a Z index from mass, like the Z as in the integer numbers that this can take. And for the Z2, it actually is almost like that, but it now can only take two values, 0 or 1. So that's why it's called the Z2 classification. And that's exactly, as you said, as just a topological index. Is that okay?
It's fine, thank you, Judith.
It's kind of like a yes or no. Is there a band topology in the system or not? And then the
question is, can you classify this model as a Z2 topological model or not?
The Kahn-Mela model?
Yeah.
Exactly. So the Haldane belongs to the Z classification, and the Kahn-Mela belongs to the Z2.
Okay. Okay,
Yes.
thank you very much. Yeah.
Yeah. Thank you for the question. Please do ask questions. Okay, so here, this topological index, as I said, because it's Z2 invariant, it can take two values only, whether it's 0 or it's 1. And then in this case, we have spinful electrons that can hop on the same lattice, and it's kind of the same model. It's just like two copies of the same model, because we have a realization for the up spins and another copy for the down spins. And that will give rise to non-trivial Z2 band topology. And as you can see now, it's kind of, if I don't have anything else in this model, it's kind of hand-wavingly easier kind of to picture that I had a copy of the Haldane model with the up spins, and now I have a copy of the Haldane model with the down spins, and they are literally lying on top of each other. This is this 2 in the bracket, what I put here. This just means that all of these bands here are twofold degenerate because of the spin degree of freedom. So upspin and downspin bands are really lying on top of each other all the time. But because they kind of have, like they connect to chirality differently. Let's say the Chern numbers that is assigned to these bands with the upspin and the downspin is going to be opposite. So what you can see here, when I actually have this second neighbor hopping and I render these bands topologically non-trivial, you can still imagine the Keenan-Miller model as two copies of the Haldane model. But now with the Chern numbers are flipped for the up and down spin. So let's say I have an upspin, and for the upspins, for example, for the upspin bands, right, I have these two bands, and for the upspin, I have the +1 Chern number down here and the -1 Chern number for the upper band. For the downspin, it will be the opposite. The -1 will be down here and the +1 will be up there. So when I actually sum up the Chern numbers for these two bands, for the total band of this in the top and the total for the bottom, it's going to be 0. So the Chern number is definitely not a good topological index to make this classification. And what actually is going to be a good number is the Z2 index, which in this case we can, as you know, before there is any kind of mixing between the up and down spin. So if no mixing here is included, those matrix elements, these off-diagonal matrix elements that would mix the up and down spin state, those are 0. And the Z2 index can be thought of as a spin Chern number, so to speak, when instead of calculating the like summing up these Chern numbers that would actually be 0, we take the staggered component and mod 2 that will give us either 0 or 1. So depending on what this number is, either 0 or 1, we have a trivial or a topological Z2 band structure. Is this okay so far? Silence. I will take that as a yes, and please let me know if there are questions. So we had for the for the Haldane model, we had these.
Judit,
Yeah.
I was trying to open up the microphone. There's no question so far.
No questions so far. Okay. All right. So these edge modes here now are also twofold degenerate, but this is what these little arrows kind of show, that we have for both, like we have both of them twofold degenerate with the up and down spin degree of freedom. So now, so far we just had two copies of the Haldane model, but and that means that as these is a preserved quantity, and therefore I can use this Z2 index, formula that we have here as the spin Chern number. But what if we have terms in this Hamiltonian that will mix the SZ component of the spin? This is actually allowed by the symmetries, and for example, something like that could be the Rajba spin-orbit coupling. And as you can see, so this is something that doesn't break time reversal symmetry, and that's an important point. So time reversal symmetry is present, and as long as it's present, the Z2 band topology is going to be preserved. And even if we mix these SZ components, and this actually is true perturbatively, because what happens is that if we just add the small Rajba spin-orbit coupling, then we will there will be a hybridization or mixing between the up and down spin bands. And as you can see, there is a little bit of a splitting here. So these bands are on top of each other for the up and down spins, but here they're kind of like shifted from each other because of this mixing by the Rajba coupling. And also the edge modes that belong to the upspin and the downspin, they're also kind of like shifted from each other. But you can still find degeneracies for these edge modes, and they would still kind of connect the top and the bottom bands, collapsing the gap in the system. And that means that these are topologically non-trivial edge modes that will be conducting on the edges, or will lead to conducting properties on the edges of this system. And yes.
Well, I have two quick questions.
Yeah.
For the Kahn-Mellon model,
Yes.
We can calculate more or less analytically these dispersions with the spin Rajba.
100%.
Yes. Are these analytical calculations?
Yeah, so what you can see here, I think this is from the original paper, right? And you can, if you have the Kahn-Mellon model with the Rajba, this is still like, for the bulk, it's a 4x4 matrix kind of. So that's even, by hand, you can diagonalize it. It's not like a huge task, or mathematical can surely diagonalize it. And for what you can see here,
periodic?
Yeah.
So we can use Bloch's theorem and stuff like that to derive these expressions.
Exactly. So for here, what you can see in this figure, why this looks so weird, right? Like you have so many bands. If you just solved for the bulk, you would have 4 bands only, because there are the spin up and spin down parts, and then AB sublattice.
So after the spin up and spin down, then can you differentiate them?
I'm sorry, here?
In these bands.
So in these bands, the spin up and spin down are not like a useful way to characterize the bands anymore, because of the Rajba term. Okay. Those are mixed with each other. Here, you could still do it. You would still have this 4x4 matrix that characterizes, when you write, your Hamiltonian in terms of these electrons, you would have like 2 sites in the unit cell. So you'd have, like, so to speak, an orbital degree of freedom, which is this A and B. And then you would have the spin degree of freedom, which is either 1/2 or -1/2, the up or down spins. And that's giving you like a 4-dimensional, or like a 4x4 matrix that at the end you need to diagonalize. So you would have 4 bands. And here you see these A and B bands, like the kind of, corresponding to the orbital degree of freedom. But these are twofold degenerate everywhere in the Brillouin zone because of the spin degree of freedom. And what happens is that you have, in this 4x4 matrix is actually 2x2 matrices. You have like a block diagonal system. And then you can, separately solve for the upspin and separately solve for the downspin, so to speak. Right, but as soon as you have the Rajba, you would have off-diagonal parts, and that would mix the up and down subspaces with each other. And then you would see like kind of a splitting here. These are not anymore degenerate with each other. But what actually is shown in this figure is the open system. So it's not the block that you see. It's actually open in one of the directions. I don't remember which one, but it doesn't really matter. Maybe I don't know. It says like KA. So I guess in the B direction, it's open, and only like one in one of the direction is the momentum still a good quantum number, right? So you have the K only in one direction. So it's like a one-dimensional system, and in the other direction, we have an open geometry, and that means that you would see, so many bands here, like depending on how what is the width of this stripe that you are trying to solve for. And this is still, I still wouldn't call it like a numerical simulation, because we would, of course, numerically solve this problem, because, these are big matrices that you can just diagonalize, so, by hand, but you would still be able to do it with, I don't know, like some mathematical or whatever. So it's still analytical, let's say, in that sense. Okay, so what?
Thank you very much.
Yes, you're welcome. Thank you for the questions. I think maybe I go too much into details. Please shut me down when I say too much details. Okay, so as long as this Rajba,
please go to the details. It's been very nice. Thank you.
Okay. So as long as the Rajba is small, this mixing is small, and as you can see here, where these bands start to move, and at some point when the Rajba is too big, they will actually close this gap. So like this band that is growing towards the gap, and this one as well, they will touch at some point. And what you can see here in this instant is that, depending on what the size of the Rajba is, at some point, this is this kind of boundary here, these bands will touch. And when they touch, there is a topological transition going through. And at that point, when they kind of like, as you increase the Rajba further after this touching point, they will again open that gap, but their topology will be changed. So they can, so to speak, exchange topological charges or Berry curvatures. And then when you reopen the gap, they are now topologically trivial. And that's actually shown here nicely, that they're also, although this is still an open system, as you can see, like, because you have so many bands here, this is still an open system, or like half open geometry. We have these edge modes because in every open system, you will find states that live on the edges, but these edge modes, they're actually topologically trivial now, because they start from one band and they go back to the band in the same kind of, how to say, like from the top band you go to the top band, and from the bottom band you go back to the bottom band. So they don't collapse the gap anymore. And because they don't collapse the gap, this is going to be, a topologically trivial phase. All right, so the Rajba is fine. We can mix the SD quantum number, but because it doesn't break the symmetry that will protect the Z2 topology, but it's only perturbatively true because if this Rajba is big enough, then we close the gap. So there are these two ways how one can preserve topology. Either like what needs to be actually there to preserve the topology of these bands. Either we need to respect the symmetry that protects this topology, which actually happens here, and we need to keep the gap open. As long as the gap is open, nothing can happen. When we close the gap, topology can change. So in this case, if the Rajba is too big, then we actually go through this topological transition. All right, and the question now is that can we have something similar for magnets and magnetic excitations? So this is kind of what we are interested in, or we were interested in with Carlo and Nick and Andreas. And for this, let me go back to the kind of models of magnets. Even in a simple ferromagnetic phase that is completely topologically trivial, like nothing about this phase is topological or topologically non-trivial. We have just an ordered ferromagnet realized on a honeycomb lattice. So this is a Mott insulator, where the electrons are sitting tight on these sides, and we have spin degrees of freedom. And when we flip a spin, that corresponds to magnetic excitation, and this magnetic excitation can propagate over the lattice, and then very similarly, like the electrons can hop over the lattice in the Haldane model, we can have these magnons, magnetic excitations, move around the honeycomb lattice in a similar fashion, and they would form exactly the same type of bands. But these bands are now the bands of the excitation, so it's not like the ground state. And right, so if we have just a Heisenberg type of Hamiltonian, when we perform these spin wave calculations, we have very similar kind of hopping terms that we would have for the electrons. And we can add Jaroszewski-Moria interaction, which is a type of an anisotropy. I don't know whether you are familiar with that or not. Maybe you have heard of this. So the DM interaction, or the Jaroszewski-Moria interaction, it comes from relativistic spin-orbit coupling. I always forget. I think it's like first order in perturbation, and it has this S cross S form as like the effective spin Hamiltonian. And this form actually, or like this DM interaction actually is usually the reason why we can have in these magnets different type of topologically non-trivial excitations and so on, or like bands of different non-trivial band topologies realized by these magnetic excitations, right? And this kind of looks like when we add these Jaroszewski-Moria interactions. So the DM interaction actually, let me add one important point. This can only be present on bonds where there is no inversion symmetry. If there is an inversion symmetry, then DM is forbidden. And as you can see, for the honeycomb lattice, on the first neighbor bonds, on these ones, there is inversion symmetry here in the middle of the bonds. So on these sides, or sorry, on these bonds, on the first neighbor interactions, the DM interaction is forbidden. Very similarly to Haldane's original model, where this complex hopping is forbidden for the first neighbors. But for the second neighbors, we can actually have DM interaction on these triangles that you can see here. And that will actually lead to the same kind of non-trivial band topology as we had for the electrons in Haldane's model. And Haldane's model looks kind of artificial, like it's harder to kind of justify why we could have these complex couplings and so on. But for the magnetic excitations, this is kind of straightforward. And in most of the materials that we actually deal with, there are anisotropies, or the symmetry allows anisotropies. And usually when the symmetry allows an anisotropy, it's going to be present. And no matter how small this anisotropy is, it actually can open this gap and render these bands topologically non-trivial. And once we have this kind of a system, then we can have, because of this DM interaction, finite Berry curvature in these bands that will actually sum up to plus or minus 1 once we integrate it over the Brillouin. Okay, so we can have non-trivial Magnon bands kind of easily, in the fashion of the Haldane's model, for example. And then one could ask the question, so okay, definitely we won't have any quantized effect that comes out of it because these are excitations. But we can still measure something that is called the thermal Hall effect, and that is related to the Berry curvature of these Magnon bands. And what happens in this experiment is that you put this sample into into magnetic field, and you apply some, or kind of realize some kind of a temperature gradient. So you heat one end of the sample while you keep the other ones colder, and because of that, there will be an energy flow. Like the magnons will follow this temperature gradient, and because of the finite Berry curvature, they will also like deflect and then change the curve of their motion. And instead of just going in one direction, there will be like a transverse Magnon current, and that is the thermal Hall current that people can measure. I heard that this is a very difficult measurement actually. Nonetheless, it's possible, and that could actually be an indication of non-trivial band topology realized by these magnetic excitation. So, okay, all right. So
do we need a spin orbit for thermal Hall effect?
So, Professor,
yes,
we have a question.
yes, please.
Is that if we do need a spin orbit for the thermal Hall effect?
We do, yes, exactly. So for these magnets, let me just come back here a little bit. Any kind of anisotropy that is present. So in fact, as it turns out, it's not just the Jarzynski-Moria interaction, not just this type of anisotropy is the one that can render these bands topologically non-trivial. There are other type of anisotropies like Kitaev type of anisotropy and so on that was shown that can give rise to non-trivial band topology, or symmetric exchange even. But the origin for every kind of magnetic anisotropy in the system, in these magnetic materials, is actually the spin orbit coupling. So if we don't have spin orbit coupling, then we would have only this S.S type of terms, which is a scalar product. And if you think about it as because it's a dot product, and the same J, right, corresponds to the X, the Y, and the ZZ component, this is fully rotational symmetrical. And because of this full rotational symmetry, we have this kind of how do you call it, kind of freedom in choosing like where the spins are pointing. And when the ferromagnetic phase is realized, then there is a spontaneous symmetry breaking, right? But as soon as we have any kind of coupling to the lattice, that can only happen through the spin orbit coupling, and that will actually give rise to anisotropic terms in this Hamiltonian, like the Jarzynski-Moria. So to be able to have a Jarzynski-Moria interaction, we actually need spin orbit coupling. But not just for the DM, for any kind of anisotropy that is there, the origin, actually, the macroscopic origin is the spin orbit coupling. Otherwise, the spins would not have any knowledge about the lattice, right? Like they would be independently, turning themselves somehow. Like they would not have like preferred axes or preferred planes or anything like that with respect to the lattice, right? So the spin orbit coupling is actually very important to have any kind of.
Thank you very much, Professor. Thanks.
Thank you for the good questions. very, very important. Right, so I show here a few of the papers that were, or like a few of the works that were considering band topology or the topology of bands of magnetic excitations. And this is not at all a full list. There are other works as well, so I apologize for not showing everyone here. But it's been like, there was growing interest in whether we can realize these different band topologies by magnets. And one interesting question that we were also kind of interested in is like, okay, so the Z band topology, the Chern numbers, is kind of easy, let's say, because of these magnetic anisotropies to realize in magnets, in real magnets. But what about Z2 band topology? Can we actually do that? Can we have Z2 band topology for magnetic excitations? And one kind of question that arises immediately is that how can we assign spins to these magnons? And okay, it's a weird question because we deal with spins to begin with, right? But if you think about it, when I have, oh, sorry, maybe this is not the best slide. Let me just go back for a sec. So if you imagine that I had, say, for example, this spin 1/2 sitting on this lattice, and my excitation was to flip a spin down to this spin -1/2, for example, as the -1/2 state, then if that was my excitation, that's kind of a spinless excitation, right? Because it's kind of, it's a featureless magnon that just, you know, can swim over this lattice. It has no other degrees of freedom. And one like a smart way that was introduced by Kondo and Katsura sensei is that we can imagine, instead of having a single layer of this honeycomb, we can imagine a bilayer system, which is very ugly in this figure, so I apologize for that. Maybe you can still see what's going on here. So we have these two copies of the honeycomb lattice, and in one of them, so like both of them is ferromagnetic for some reason, and because either we have ferromagnetic interactions or some other cases, and we have this ferro order in both of them, but for the kind of the bottom sublattice, we have the spins pointing in one direction, and for the top, we have the spins pointing in another direction. And that can be actually realized if we have an ontoferromagnetic coupling between the layers. And then this would be like a happy ground state for such considerations. And now if we think about it, that we can, you know, kind of, for just like one dimer here, like if I choose a dimer here that for which like one of the sides belongs to the bottom and one of the sides belongs to the top lattice, then we have this kind of configuration, and we can have an SZ +1 transition by flipping the down spin up, or we can have an SZ -1 when we flip this up spin down. So we have a spin degree of freedom, so to speak, just because we have these two differently oriented layers, and then flipping a spin up or down would correspond to different kind of magnetic excitations. And we can think about that different kind of magnetic excitations as having a spin degree of freedom assigned to these magnetic excitations. Another idea was
one small question. Sorry for interrupting.
Oh, please.
So this coupling here is only between the sublattices A or the sublattices B.
So we have coupling everywhere, right? So between so sublattice A and B, say like A1 and B1, they belong to the first layer. And A2 and B2, they belong to the second layer. It's a very ugly figure. I apologize for this.
No, it is good.
Okay, so any coupling between, say, like AI and BI is within the layer. And let's assume that those are ferromagnetic couplings. So the spins wants to point in the same direction with respect to each other. And if we have a coupling between 1 and 2, say like A1 and A2 and B1 and B2, that coupling is going to be antiferromagnetic. So the layers with respect to each other want to be aligned oppositely.
Okay. Oh, thank you.
Okay. And here what you can see is like layer 1 and layer 2, for example. And like, say the bottom layer is downspin and the top layer is upspin. And then I can imagine for this kind of like dimer that belongs to, this kind of living between the layers. Like depending on which one I flip into which direction, I have either an upspin or a downspin excitation, let's say, thermologically, or like hand-wavingly. That's kind of how we can think about it. Is this okay?
Yeah. It's okay. Yeah.
Okay, super. Thank you so much. Right. So a very similar scenario is if we consider a bilayer system where the strong interaction is actually between the layers. So let's say that we have a dimerized system where these layers are strongly coupled with each other. And in that case, we can, instead of thinking of a side factorized kind of solution for these dimers, we have to treat them quantum mechanically entangled. And a good ground state, for example, for this antiferro coupling between the layers would be a singlet covering of this lattice. So the singlet is the ground state, and we can think about the excitations as the triplets. So for example, I could have an SZ +1 triplet when instead of a singlet state, I have the up-up state, or instead of the singlet, which is a non-magnetic state, I have the down-down state for the SD-1 excitation. And then I would have an SZ0 excitation as well that belongs to the third triplet, when instead of here having a minus sign, I would have a plus sign for the up and down configurations. Okay, so then in this case, that excitation, that magnetic excitation that we talk about, it doesn't just have kind of like a spin flavor, but it really is kind of like a triplet. It has like 3 flavors, as the +1, -1, or 0. So these triplets, they, among these triplets, we could select the ones that are time reversal partners, and these would actually realize the spin degree of freedom. And for another kind of example that I work with Carlo on like forever, and it's never going to be finished, I think, is instead of considering a dimerized system, with magnets, what's nice that we can actually consider a compound that is built of nickel or vanadium or some other magnetic ion that can actually carry a spin 1 instead of a spin 1/2. And if we have a spin 1, and say, for example, we have, I don't know, a large a single ion anisotropy that favors the small spin state, then we could have an SZ0 ground state realized everywhere because of this anisotropy, and then the magnetic excitations would correspond to changing this SZ0 state into their plus or -1 state, and those are actually also time reversal partners, and they could actually realize the spin degree of freedom for these magnetic excitations. So we can have different scenarios that would actually lead to magnetic excitations to which we can assign some sort of a spin degree of freedom. And in that sense, that there's kind of like, this question whether we can have Z2 band topology or not is now, maybe a meaningful question. Okay, and a proposal for kind of experimental fingerprint for such a systems would be the Magnon spin-Nernst effect, when we have kind of these 2 antiferromagnetically coupled layers in the original model. One of them is aligned up and the other one is aligned down, ferromagnetically coupled to each other, right? So between the layers we have this antiferro coupling, and now again we apply a temperature gradient, and instead of just having kind of like current along this temperature gradient, we would have, because of the spin orbit coupling or the anisotropies in the system, we would have these spins kind of moving also to the left and the right, depending on whether this excitation is an upspin or a downspin. And as you can see, if I have a downspin excitation that moves to the right, and the the upspin excitation moves to the left, so we would have kind of like this spin separation, or kind of like a spin current perpendicular to this applied temperature gradient, and that's called the Magnon spin-Nernst effect. And this would be something that probably one can measure in an experiment if there was such a system. Right. So here is the problem. So these kind of excitations that can realize the spin degree of freedom, so to speak, for these magnetic excitations, these are time reversal partners, but they are not Kramer's pairs, right? Because these magnetic excitations are bosons, so they're not going to be like the electron spins that form Kramer's partners or Kramer's pairs, and that means that the time reversal operator that is assigned, or like that is written for this excitations, this actually squares to +1. So this is not, it's most probably not going to be able to protect the Z2 band topology for this system. And what we set out to kind of investigate is like what happens even if you can have like Z2 band topology, how robust it is actually, and what is the symmetry that could maybe protect the Z2 band topology. So that's why the title was Z2 or not Z2, whether we can really have this Z2 band topology or not. Okay, so we consider, instead of the honeycomb lattice, we consider a Kagome lattice because it's more complicated, or I don't know why we actually considered that, but this was our choice. And we have a bilayer Kagome lattice. The Kagome lattice is built of triangles that are connected by the corners, and we have 2 layers of that. And again, the strong interaction, the strong antiferromagnetic interaction is going to be between the layers. So these numbers that you can see here, they kind of show the strong coupling. And
Judit,
yes, please.
one small question.
Yes.
Could we please just really quickly review the spin Nernst effect? Just really quickly, what is happening in the spin Nernst effect? Because I always wonder if actually the spin Seebeck effect actually exists. I mean, it can exist by symmetry, but I
Mhm.
don't know if there's a real confusion between the spin Nernst effect and the spin Seebeck effect. I have actually in Japan, when I
Yeah.
visit Tsukuba, I have seen the spin Seebeck effect like measured, but I
Yeah.
don't know if there's maybe the same as the spin Nernst effect. So can we go to this slide and see what's going on there?
Okay, can you remind me about of the Seebeck effect, please? I know that somehow these are all connected to each other. It's kind of like,
Yeah, I mean the spin Seebeck effect is an effect that when you have a spin voltage, or I mean when you have a temperature gradient, you produce a spin voltage.
that seems very, to me, this is kind of the same as what is called the spinors here.
Okay.
Isn't one of them the opposite? Like when you have, somehow you separate the spins and that will lead to some kind of, I don't know, current or something.
It's exactly. It looks like it's the same. So you apply the temperature gradient.
Yes,
The
exactly.
temperature gradient. Why? What is the mechanism by which this temperature gradient separates the spins?
No, it's not the temperature gradient that is separating the spins. So if you just have kind of like a trivial system, there is no topology in the system, like whatever spin orbit coupling, or I don't know, like the rules for this band topology. So you just have this temperature gradient. Then what would happen because of this temperature gradient, that is like one end is hot and the other end is cold of this sample, and then there would be, because of this temperature difference, a current of magnons, an energy current, let's say, or a heat current started, right? Because of this temperature gradient that would flow from the hot to cold, kind of. And you would have, these magnons would just propagate in the direction of this gradient, right? But because there is spin orbit coupling in this material, and it's kind of, affecting these magnetic excitations, because of the spin of these magnetic excitations is opposite, the spin orbit coupling is kind of affecting them in an opposite way. And one has, for example, one couples in a way that it has kind of this, how do you call it, deflecting in one direction, and the other has a deflecting in the other direction because the spin is pointing down. I don't know if you can see my hand, because I'm kind of like showing with my hand what happens, but I'm not sure if it's actually visible.
Yeah, I can see it.
Okay, so like, for upspin, we would have like a deflection that is like that. And for downspin, it would be like this, right? That's like oppositely affecting the two spins. And so because of that, because you would have transverse component as well, the magnons are not just propagating over the lattice, but there is also a transverse component to their movement. And because of their opposite spins, they are oppositely affected by the spin orbit coupling, they would deflect into the opposite directions. And that's why, for example, on this side, you would end up with the upspins, and kind of here you would have with the downspins, or the upspin
So
excitation.
the temperature gradient, so of course, will displace the spins, but because of the spin orbit induced chirality, maybe if you break
Yes,
into
they
the same
would,
orbit, they will be affected in different ways.
exactly, and they would turn different in the different direction. But what actually drives this whole thing is the temperature gradient. So that's kind of starts the current. But then this current is affected by the spin orbit coupling, and it kind of makes the upspins move in one direction and the downspins move in the other direction. That's why it separates the up and down spins. Is it okay?
Yeah. So
You
then
know,
I can say, or we can say that spin thermoelectricity
mhm.
is well driven by temperature gradients as the topology of the members. Is that a?
Yeah, plus exactly. Plus you, because of the topology, you have this anomalous velocity as well, right? And then that component is actually different for the up and down spins. Very similarly, if you kind of think about the Chern bands and the Hall effect, in that case, you have, or like Magnon Hall effect, right? Like for the Magnons, the field, kind of like the gradient stuff that stores the current is the temperature gradient. For the electrons, you would have here an electric field, right? Like an electric potential gradient. And that would start the current, but the Magnons don't have charge. They don't have electric charge, so you can't do that. You need to apply temperature gradient to start an energy current in the system. But for, like, if you just consider the Haldane model, for that you need to break time reversal symmetry, and you apply a magnetic field perpendicular to this gradient of temperature, and that will actually create, like, make the Magnons deflect and go, like, you know, depending on whether the field is like this or like that, you would have some kind of a chirality, some kind of a normal velocity in one or the other direction. And if you flip the spin, if you flip the direction of the magnetic field that is applied perpendicularly now, if you flip it to the other way, then the Hall current would also change sign. And this is very similar. It's just like, instead of having magnetic field, you have these local spins, kind of. Does it make sense?
Yeah, it does. And one last question. That
Yeah.
tensor alpha XY, what does it stand for again, please?
This is this spin-Nernst coefficient.
Spin-Hall thermal conductivity or something? Or?
Yes, exactly. The Nernst coefficient. Yeah, it's like the kappa XY for the thermal Hall conductivity, but it denoted with alpha XY. It's what people would measure, I assume, in the experiment.
Okay, thank you very much.
If this was measured. Thank you so much for the questions. I know I'm not going into enough details. Okay, so we have this kind of bilayer Kagome system that we set out to investigate whether we can have this Z2 or not Z2 band structure. And as long as the antiferromagnetic interactions are strong, or the strongest on these dumbbells, the ground state is going to be a singlet product state. One can kind of justify it in a way that if we start from the weak coupling limit, or like the limit when every gray and black interactions are 0, then we have a completely decoupled dimer system. And one can even, you know, by hand diagonalize a 4x4 matrix of the two spin 1/2s, and then realize that the singlet is actually the ground state as long as we have an antiferromagnetic interaction. And the triplets are, you know, J away, with J is the Heisenberg exchange, away from this singlet state. So these are the excitations, and these excitations, as long as there is no coupling between the dimers, they're just going to be localized. So we would have like a 3/4 degenerate flat band. But as soon as we include interactions here between these dimers, and these interactions are small and they're weaker than these the interaction on the dimer, then the only thing that would happen, right, like on a mean field level, because the local spin of a singlet is 0, they would have no effect on whatsoever on the ground state. When the strength of this interaction is comparable to the interaction on the dimer, that will actually lead to a different kind of magnetic ordering instead of this disordered single ground state. But as long as these excitations are weaker, as long as these interactions are weaker, we have the singlet covering of the lattice as the ground state. And we would like to see if we can have something like the Kane and Mela model. We can realize something, you know, with these triplet excitations that looks like this. So we have these spinful excitations, the SZ plus or minus 1 triplet, and these are non-Kramer's time reversal partners. And we are interested in the question if there is some kind of a symmetry similar to the time reversal symmetry that would protect the Z2 band topology. So first we need to construct a Hamiltonian that is suitable for this model. And we actually start with the symmetry analysis because there is no, up to my knowledge, real like Kagome lattice that has this strong antiferro coupling between the layers. There are bilayer Kagome materials, and one of them is actually the calcium chromate is considered to be a spin liquid, but it has actually ferromagnetic couplings between these dimers, I think. So and it's a lot more complicated than the system that we are now considering. But this is just a toy model to actually, you know, see what can happen. So we look at the symmetry of this system, and in the best case scenario, it's the 6-age point group symmetry that will allow a lot of anisotropies already. And I will just add here as a footnote that so this D6H is the symmetry of this lattice that you can see here. In a real material, these sites would be my magnetic ions that carry the spin. Usually around these magnetic ions, I would have some kind of a Ligand field. And that could lower the symmetry even further. So like instead of D6H, I would maybe have, I don't know, a 3CB or something else, like a lower point group. And that would allow even more anisotropic terms than what we will have here. So this is really the best case scenario, the least anisotropic terms possible in the system. But in a real material, probably this is actually the case is actually worse, and we have more anisotropies. So first we have the Heisenberg type of term, or this XXZ type of term on the dumbbells, which is between the dimers. And also on the dimer, we can have what we call the nematic interaction. And I don't know, maybe nematic is not the best name for it, but we started to call it that for some reason. How you can think about it is that we have these Q operators, which are second order in spin. This is going to be, between so like these kind of interactions, they live on this dimer. So we have, if we wanted to classify, I don't know how much detail I should go in here because I could go on forever, and I'm really sorry about it. But you can kind of think about it as like, I have these two spin 1/2s that live on this dimer, and for the spin 1/2s, if it's just by itself, then I would not be able to have a so-called quadrupolar operators, or only the dipolar ones. So only the spin degrees of freedom are there. But as soon as I consider a pair of them, so like the same way as I consider this dumbbell here, which contains two of the spin 1/2s, we can actually have higher multiples, and the quadrupole is one of them. And this actually comes on top of, like, as a new degree of freedom on top of the dipole degrees of freedom, the spin XYZ components. I can have this other like 5 different components, but the ones that actually will be interesting for these dimers, or are allowed for these dimer systems, are the ones that are the XY components. So the quadrupole XY and the X square minus Y square component that have this form here. And why these are allowed, again, is because I have two sites, the kind of the J1 and the J2. Sites for the J's dimer 1 and 2 means the top and the bottom layer. Okay, so this is what they look like. And we can have this multiplied with a vector, because of course this kind of bold faces means that this is a vector of these two components. And then I have this nj vector in front of them that depends on which kind of side, or like which dimer we are on. This points somewhere in the real space, and then we will have kind of like a mixture of these quadrupole or nematic interactions. Maybe this is too much. Sorry. Right. Okay. But in any case, this is just monotic anisotropy. It's also called sometimes in the literature the symmetric exchange anisotropy, as in the Jarzynski-Moria is called the antisymmetric exchange, and these are type of the symmetric exchange anisotropies. Right. Okay. So now if we consider the interdimer interactions, the interactions that are between the dimers, then we can have again an XXZ type of interaction that kind of is like the Heisenberg Hamiltonian, or like a Heisenberg model, but it's not Heisenberg because it doesn't have the SU2 symmetry, because the in-plane and out-of-plane J's are not the same. And then we can have Jarzynski-Moria interaction. So now the first neighbor DM is allowed, because for the Kagome lattice, these are not an inversion centers, these ones. So we can have Jarzynski-Moria, which is this S cross S type of anisotropies in both layers. And as you can see, these little arrows here, the pink arrow, this is showing where this D vector is pointing, and the symmetry will dictate where this D vector is pointing. So what kind of anisotropy terms you can have. And in both cases, so this is the top layer, and the lighter color is the bottom layer, as you can see here. Right. So then in the top and the bottom layer, the Z component, which is this X, is pointing in the same direction for both layers. The in-plane component, the arrow that you can see here in the XY plane, this is pointing outwards for one of the layers and inwards for the other layer. So it's pointing in the opposite direction. And that actually will result in a cancellation of the contribution of this DM term in the linear spin wave formalism. So up to linear order, these actually not going to be affecting the triplet excitations whatsoever. Right, we could also go to second neighbor terms as well, and then we can have second neighbor Jarzynski-Mori interactions again in the same way that the z component of these d vectors is present, but the xy component is opposite. So in the linear spin wave theory, this actually will cancel. Okay, and then we can have very similarly on the first neighbor bonds and also on the second neighbor, but we actually like, I think in the paper we collected them, but we don't, they're not necessary for, you know, describing the topology of the system, or like they don't change much the topology of the system in the sense that as soon as we have like the first neighbor, the second neighbor will be kind of similar, but renormalizing the first neighbor effects, right? So the first neighbor symmetric exchange anisotropy has this form, and again we have these Q quadrupolar kind of components very similarly, but now between I and J dimers for both the 1 and the 2 sublattices. Okay, and then we can have of these, we have both the ones that are related to the XY, so the in-plane kind of part, and the out-of-plane part, the XZ and the YZ parts as well, or components, right? Okay, and this is how one can kind of picture what these look like. You know, if you think about kind of d orbitals or representations like that, then this would be like from the top view for these nematic anisotropies, and these would be the XZ and the YZ components, or how they mix. But this is way too much, I think, and it's like not so very interesting. But what actually I want to tell you is that the Hamiltonian that is allowed by the symmetry is a beast. There are a lot of components and a lot of different, you know, coupling constants here that are allowed and are most probably present if we have a material that has this bilayer Kagome structure. So even if we don't consider, you know, like a horrible case when there is a Ligand field around them that actually would even further decrease the symmetry, and that will allow for even more different types of anisotropies. Okay, so this is the full Hamiltonian, and I will collect it in a more kind of understandable way, hopefully. So instead of having this XXZ anisotropy, I will consider that the J perpendicular and the J parallel are the same, because this doesn't do anything with the topology of the system. So I will just consider a Heisenberg Hamiltonian, which has the full SU2 rotation symmetry. The Jarzynski-Mori, as I said, the in-plane components will cancel, so we only have DZ. And the DZ is actually only selecting kind of like one axis along the Z direction, and we still have a rotation symmetry in the plane. So there is still like a U1 rotation symmetry. So as long as I only have the Heisenberg term, the system has full rotation symmetry. When I switch on the DM interaction, I break this or lower this symmetry down to the U1 symmetry. And now if I add nematic interactions, those symmetric exchange anisotropies, then I will mix the spins with each other, and I will break the U1 symmetry. And additionally, I can switch on magnetic field that will break time reversal symmetry as well. So depending on how many of these anisotropies we have in the system, we can lower the symmetry. So let me just begin that the ground state is this singlet covering of this lattice. And then we can have excitations that correspond to the 3 triplets. So on each side, we can create 3 different types of excitations, and then those can propagate over the lattice. And that will actually result in a big matrix if I want to, after doing linear bond wave formalism, which is not so very important. It's very similar to the spin wave formalism when we flip the spin down, and we were describing kind of like the propagation of that spin over the lattice, or the spin flip over the lattice. We now think of like the excitation as breaking up a singlet entirely, and instead of the singlet putting down a triplet that can move around the lattice. And we have like, because in the Kagome, we have 3 sides, A, B, C, like 3 dimers in this case. In the unit cell, we have these 3 orbital degrees of freedom, A, B, and C. And we have also 3 spin degrees of freedom, the +1, the -1, and the 0. So it's a 9 by 9 kind of matrix. And how we actually separate it and make it a little bit simpler and even easier to digest is that we have a spinfold part that you can see here with this sigma And I think this is probably going to be too much, I guess, for those that who are not familiar with monadic excitations and so on. So please shoot me down anytime if you feel like it's too much. So okay, so what I want to write up here is this kind of, it's very similar to the hopping Hamiltonian that we had for the Haldane model and the Keenan-Miller model, but now for the triplet excitations. So it's kind of like a hopping for the triplet. If you think about it, I have a T dagger here, which is creating a triplet state with the sigma index that is either the up or the down spin, and that is connected somehow with the T. So these are the T dagger T type of terms. And we have also pairing terms that are described with these N matrices, but those are not so very important from the point of view of the topology of the system. Right, so we separate the triplets that have spin, as we call them, the spin-4 subspace, which is the up spin triplet and the down spin, so the up and the down state, and the T0, which is the spinless triplet. This is not mixing with these guys, as long as the symmetry is this the 6H and up to the linear order. So if I had a magnetic field, for example, that is not pointing in the Z direction, but in the X or the Y direction, that would actually mix these subspaces as well. And further on, isotropies could mix these states as well. So if I had lower symmetry, then there would be some kind of a mixing, but not in this D6H kind of symmetry. So in that case, I can actually think about this subspace, the spinless subspace, as something entirely separate and focus on this one. So these are going to be not affected by any kind of symmetries, and usually they remain trivial for that matter. And where the actual fun goes through is actually the spinful part, where we have these up or down triplet excitations. Right, and just to explain like what these boldface T dagger means, it's kind of, as I said, depending on like what we have, it's like the spin for the T1 and the T-1 state for the K momentum. And within these T1 and T-1, which is kind of, we can denote it as with M, right? So the M can be 1, -1, or 0. This is the 0 subspace. We can have A, B, and C type of triplet, depending on whether we created the triplet on dimer A, B, or C. All right, so we have these two decoupled subspaces, the spinful and the spinless subspaces. And this is the trivial part, and this is where we actually will expect some kind of non-trivial band topology. And these matrices, the M and the N, the M is kind of the hopping matrix, and the N is the pairing terms. It's very similar to superconductivity, right? The M and an N, these are similar. And they mean that it means that they only differ in their diagonal parts, so one can actually diagonalize them simultaneously. And these are 2 by 3 size, which means that we have, so it's like a 6-dimensional kind of subspace, because we have 2 spin degrees of freedom, like the +1 or the -1, and 3 orbital degrees of freedom, the A, B, and C. Okay, so yes, as I said, this is the spin, and the 3 is the orbital degree of freedom. Right, and then we can kind of try to see what happens in the case when there is no nematic interaction. So we only have the U1 symmetric case, which means that we have these XX-Z type of interaction, and we also have the Jarzynski model. But let's start with the XX-Z. So I will write this M matrix for the spins, for the triplets, sorry. The first part, which is describing the spin degree of freedom, is actually an identity matrix, right? Because I don't care about whether this is up or down triplet, the Heisenberg term or this XX-Z term would look exactly the same for all of the triplets. And the second part, sorry, the Jarzynski-Mori interaction, for the spin part, I have the SZ matrix, which is kind of the SZ, the Z-polar matrix, describing right, that what happens with the up and down triplet excitation. So why this is actually what I see, or like, how this makes sense, that this is the SZ, is that it has like a plus sign, for example, for the upspin, and the minus sign for the downspin. It doesn't mix the up and down spins, right? Because it's still a diagonal matrix with plus and -1 in the diagonal, but it affects the up and down spin in an opposite way. So this is actually why this deflection to the opposite direction comes from, because the chirality is going to be opposite for these up and down triplet states. And that makes total sense, because this SZ is right. It has the +1 for the up and the -1 for the down triplets. And very similarly, the U1 would be actually still there if I had the magnetic field in the Z direction. And for that, again, I would have the SZ matrix here. So this is diagonal in spin space. All of the terms up to the U1 symmetry is going to be diagonal in spin space. And there's no mixing between the up and down triplets. So this would be like completely, how to say, a block diagonal kind of system that we could solve very similarly to the Kahn-Mela model without the Rashba term. So this would exactly look like that, formally as the Kahn-Mela without the Rashba term. So this is the symmetric case when we only have kind of the Heisenberg type of interaction, and then we have these degeneracies right at the gamma point and the K points. And this is just a usual Kagome band structure that we would have for a Kagome lattice of electrons, for example, that would hop on this lattice. But now we have triplet excitations hopping on this Kagome lattice. And we look at this lattice from the top view. So please don't forget that these sites are actually dimers, and triplets are living on them when you make these excitations. So that means that because we have these triplets, we have 3 spin degrees of freedom, the +1, -1, and the 0. And that these 3-fold degeneracy that I denoted here is exactly corresponding to that. So we have all of these bands, all of these 3 bands are 3-fold degenerate with the spin degrees of freedom. Right, and that is because of the spin rotation symmetry of this first term. Now, if we break the spin rotation symmetry or lower it to U1, then the Djorzhinsky-Mori interaction will actually split the up and down spins, right? So we will have, or like, sorry, it will not split the up and down spins, but it will affect them the opposite way. And it will also, very similarly to the Haldane model and the Kahn-Mela model, we will open the gap at the K point, and also in this case for the Kagome lattice, we will open the gap at the gamma point as well. And the gapless stuff that you can see, this is actually the T0 triplet, the SZ0 triplet that is not affected by the DM interaction whatsoever. So just to have like a clearer picture, I plot here the SZ +1 and -1 triplets, and those are the ones that are actually gapped by the DM interaction. So this looks exactly the same as the Kahn-Mela model would look like for the Kagome lattice. And we have this 2-fold degeneracy that corresponds to the spin degeneracy in the system. Okay, so there is no mixing, and then we can have the up and down triplets completely separate from each other. Right, I don't really want to go into details for this one because it's not so interesting and not so closely relevant, I guess, for this, but one can play with the Djorzhinsky-Mori interactions, the first and second neighbor interactions, and then changing the strengths of those, we can realize band touchings of these bands, and then kind of exchanges of topological charges, and then go between different kind of topological non-trivial band structures. Right. Okay. I will, if you don't mind, because I think I'm going very slow, I will just skip this part where I kind of describe like what happens in this case. But let me just show these figures here that depending on where we are on this kind of topological phase diagram, let's say, we can have different kind of Berry curvatures, before and after these band touching transitions. So this is exactly what you can see here. The red and the purple one is showing whether it's red or purple, it shows the sign of the Berry curvature, and the kind of the color is the intensity. And as you can see, where we have this quadratic band touching transition, the intensity of the Berry curvature is actually concentrated around the ring, and is the strongest around the ring. And when we, in this case, when we go through this kind of band touching transition point, we actually close the gap at the K point, and we leave the gamma point open. And therefore, the Berry curvature around the gamma point will not change at all. But at the K point, after going through this transition, we will close the gap. Then there will be some exchange of topological charges, and then we open the gap again. And as you can see, what was plus is now minus, and the minus is going to be plus. And then when you add up the Berry curvature, right, for these bands, like for this one, we have a +1, so like M is 1. Then for this middle band, we have a contribution from this negative Berry curvature and the positive one. So when you integrate for the entire band, it will be actually a 0. This is what you can see here. And the the top band has opposite, so that's negative because it's the purple one, and that's -1 when it's integrated over. And if we go now through this band touching transition along this line, and we close the gap and we open it again, and these topological charges are exchanged, then we didn't affect the bottom band curvature, so that's going to remain the +1. And here now we have only blue or like purple, and that will sum up to -2 for the middle band, and I will have a +1 now for the top band. So that's kind of what happens here, right? And then there is some kind of a way to, to project this system to this 2x2 kind of problem around the K point and expand around the K point and have this analytical description for the Berry curvature that is centered around these points and so on. But I don't want to go too much into too much details about that because it's a lot. Okay, and then of course, depending on like if we cross this other phase transition, like topological transition line, then we can close the gap at the gamma point and exchange topological charges at the gamma point. And in that case, the top band is not going to be affected at all. Okay, and then one can have a very similar description for this band touching transition at the gamma point, but now we have to go to higher order in the expansion because it's a quadratic band touching. It's not a linear band touching as in the case of the K point. Right, okay, and I will not detail this if you don't mind because it's a lot of analytical stuff, right? Okay, so if we had finite magnetic field, then we would break the time reversal symmetry. And for a time reversal symmetry broken case, one would expect some kind of a churn physics going down. And this is exactly what happens. So we had originally these 3 bands, or like 3 band, I don't know how to call it, maybe clusters or something, on top of each other. They were all on top of this gray one, which is the middle one, the T0 triplet, right? And if they're on top of each other, because there is no Zeeman splitting, then there is this degeneracy that I was talking about. Now, if we have a finite magnetic field that will Zeeman split the triplets, and the SZ +1 triplet will move down in the field, and the SZ -1 triplet will move up in the field. So we will have this Zeeman gap kind of between the triplets. And this is the first figure. What you can see here is the bulk case when we have the kind of periodic boundary conditions in both the X and Y directions. And for the other panel, you can see the open geometry when we have only like one, in one direction, the system is periodic, and in the other direction, the system is open. And as you can see, for the -1 and the +1 triplets, the Chern numbers are opposite, right? So this is exactly as one would imagine for like, when I was talking about the Kahn-Mela model, and I was saying like, you have these 2 band structures and they both degenerate with the spin degree of freedom, but the upspin and the downspin have opposite Chern numbers. That's exactly because of this opposite type of chirality that the up and down spin have, and they have these opposite Chern numbers, and if they were on top of each other, right, those Chern numbers would cancel. And the Chern number would not be the good topological index that would characterize, the band structure of these systems. But now we have Zeeman splitting, so they're not on top of each other at all. And these actually, +1, -2, and so on, Chern numbers are going to be there in these bands, and correspondingly, right, in these gaps, sorry, that are like non-trivial gaps, we would have these edge modes as well be present. Okay, so now if I go back to the Z2 classification, when there is no magnetic field, then these +1 and -1 triplet bands that are fully on top of each other everywhere in the entire Brillouin zone. And that means that, in that case, and as I said, for the top and the bottom, the up and down spins, we would have opposite Chern numbers, and the total Chern number would be 0. But because of these opposite Chern numbers, if we calculate the Z2 index using this spin Chern formula, this would actually be finite. So we would have like a +1 for these bands, a 0, and then a +1 again for the bottom band. And because of that, correspondingly, we would have these helical edge modes appearing in an open system, where we have, say, for example, in this case, this is the geometry that you can see. Like we have a periodic boundary condition in one direction, and the system is open in the other direction. And on the open edges, we have a spin current, right? Like these spins these edge states that have kind of like spin flavor, right? For the upspin, for example, it goes in one direction, and for the downspin, they are propagating in the other direction, and so on. Okay, and kind of one can see it from this figure. I don't know how much one can see it from this figure, but let's say I have this, like on one edge, I have this dark red colored spin, and on the other one I have, on the same edge, I have this dark blue color spin. And then, for example, the dark red one is this edge mode here. At some given energy, it has a slope that is, say, positive in this direction. So this would go into the positive direction. And then for the blue one at the same cut, I would have a negative slope. So that tells us that, the group velocity of this mode is the opposite direction. So they would actually, although they are on the same edges, they would propagate in the opposite direction. All right. Okay. So, right. So the question is, I have this system, and it looks exactly like the Kane-Mela model realized by magnetic excitations, with these helical edge modes that now have spin flavors, and they would propagate right in the kind of opposite directions on the same edges. What happens if I add nematic interaction? So if I add this additional nematic interaction to the system, right, then what will happen? Is it the same as the Rajba term in the Kane-Mela model? Like, will I have that kind of protection that the Z2 band topology in the Kane-Mela model enjoys, or not? And the answer to that, like, is kind of the simplest way to answer that question is to look at what happens with the edge modes. Right, so for the Kane-Mela model, this is what happens to the edge modes. We still had, for a small Rajba term, we still had these edge modes that are kind of crossing, like going from one band to the other, so like collapsing the gap. And these were topologically non-trivial. But unfortunately, when we add these nematic interactions to this magnetic system, then these bands, or like edge modes, they become topologically trivial. So as you can see, the edge mode that starts out from the purple band, it goes back to the purple band. It doesn't cross anymore over to the red band that is the top one. So that means that there is actually this hybridization between these bands and or like the up and down triplets, and it happens in a way that actually these Z2 band topology will be vanishing. And what we were then kind of asking, okay, so why is this the fate of the Z2 topology? Why the nematic term actually is breaking this Z2 topology? So I'm sorry. So we were kind of trying to come up with a pseudo time reversal operator that behaves the same way as it would, the time reversal operator would behave for the Kane-Mela model. So we kind of constructed it, an operator that would, return in this for these triplets, this would square to -1. So this would kind of look like a time reversal symmetry, but it's not the real time reversal symmetry. It's the time reversal symmetry multiplied with this SZ matrix, which is kind of the U1 symmetry. So that looks something like that in this subspace, when we have the I2 is kind of the kind of particle hole subspace, and the I times the sigma Y is the spin subspace for that the up and down triplets, and this I3 is a 3x3 identity matrix describing the orbital.
Sorry, Professor Judit, we just have a few minutes left because there is another conference in this room.
Yes.
So,
I will wrap it up, and I think it's anyway too much. So I'm sorry about that.
Thank you very much. I'm sorry.
Sorry. Okay, so we have this other TR operator that we think that could protect this Z2 topology, but it's actually not the time reversal. It's the time reversal times the U1 symmetry. And if we collect, like how these different operators, like U1 or symmetries, the U1 symmetry, the physical time reversal symmetry, or this time reversal symmetry behaves for all of these different types of interactions, then for the physical time reversal, only the Zeeman will break it. For the U1, the nematic breaks the U1 symmetry. And that because of that, there's a lot of math here that you don't need to know. Because of that, the nematic terms, these quadrupolar terms, they will actually break the pseudo time reversal symmetry, which means that when we have, like this symmetry operator that we can cook up that could protect the Z2 invariance, this will not commute with the terms that are from the nematic interactions in the Hamiltonian, which means that, as soon as we have a nematic interaction, that will actually break the pseudo-time reversal symmetry and will, end the Z2 topology in this triplet. So that's kind of the takeaway. I think here I will actually stop. So although this is a good idea to realize, Z2 band topology with monetic excitations, these are actually fragile, and they are not protected by any kind of symmetries. And it's not just a property of the Kagome lattice. It's also present in honeycomb lattices and other magnons for bilayer systems and so on. So like there is maybe, one could ask, like, is there a way to have a system where we could have these pseudo-time reversal symmetry to be inherent to the system, or is it always going to be broken by some anisotropy terms that are not really present in these magnets? And that's kind of a question for the future. And I will stop here. I'm sorry, this was too long. Oh no, I didn't want to stop sharing.
Thank you very much, Professor Judit.
I wanted to show this last picture and thank you and wish you the holidays.
Oh, thank you very much.
Sorry, this is the Grinch.
So, Professor Judit, there are no questions. So, this is the section for the questions, and we are waiting for something that have one.
Okay, I'm sorry that it was too long.
No, it was amazing as always.
Thank you so much for saying that. It was too long. I'm sorry. I should have,
Don't worry, Professor Judit. So, in the audience, there are any questions? At the Zoom meeting?
No, in the Zoom meeting there are no questions. So here in the inside meeting, is there any question? So apparently we asked all the questions during the presentation already.
Yes.
I was the translator. So now, Pedro, you were going to ask something, Professor Judit?
Yes, Professor Judit. So, could you share your presentation with our group to review or your reference and your topic to try to learn more about that type of topics?
Oh, absolutely. I can make a PDF and send it over to you if that's okay. Would that work?
Thank you very much. So since Pedro will start his internship soon, he would like to review this topic. I will sit down with him to review them.
Okay.
So it will be important for us to be able to, I don't know if to recalculate, but to at least go deep into some of the Hamiltonians, the symmetry part, the Kagome part. So
Yeah. Yes, I think it's like maybe it's not the best idea to start with the Kagome. I don't know. Maybe like another system would be better. I don't know if you want to just get familiar with the formalism.
okay,
But it's up to you. I would be happy to send it in any case, but this is a mess because it's 9 by 9 times 2 because there is particle hole symmetry.
oh,
But I'm happy to send it. It's just perhaps not the best starting point, let's say. But of course, please feel free. And also, if you have questions, just shoot me an email or something.
sorry, Judith. I didn't hear what you just said. Can you repeat, please, one last time?
Yeah, sorry. I was just saying that that perhaps the Kagome is not the best starting point, I would say. Like if you're not familiar with this stuff, but if you want, I would be happy to send the presentation, and also if you have any questions, just send me an email, and I would be happy to discuss as well.
Okay, yeah, but maybe we can start with the Kahneman model.
Yes,
as you did. And okay.
Yeah, just do the Kahneman because for this one you need to learn a lot about like generalized spin wave formalism and stuff like that. So by the time you get to the point where you can analyze this matrix or the triplet Hamiltonian that you get, like you need to do a lot of a lot of extra steps. So I would start with beginner.
Okay, Judith, thank you very much.
Super, thank you.
Really,
Thank you.
really appreciate it. Thank you very much for your time.
Sorry for
I-
talking so much.
No, it was very nice. Wish you a happy holiday.
Happy holidays to you too.
Send
Have a
my
nice-
regards to Julia, to your sister,
Thank you.
and we will see you on another chance, okay?
Super, thank you so much. Thank you, take care.
Okay, so here, Unipamplona says thank you to you. Thank you.
Thank you, bye-bye. Thanks for being so patient.
Bye-bye.
Bye. Bye, see you.